In this project, we are going to investigate the performance of LCNS with Visual-Inertial Odometry for Lunar Rover navigation. The objective is to investigate possible performance increase using LCNS and GNSS with current visual and inertial techniques used in Lunar Rover navigation. We are going to look at the satellite-based navigation methods and their limitations. We're going to go over visual odometry and some open source libraries. We will present some open source planetary datasets which we are going to base the evaluation on. Moreover, we will present you the framework we use for the loosely coupled fusion, and lastly, we will showcase the results and finish off with some remarks on future plans. So in order to navigate on the Moon, there are two methods proposed at the moment. We can use GNSS signals coming from Earth. However, this also comes with geometry issues since all signals are coming from a certain direction. Then there are certain locations on the Moon which are not visible with GNSS, making the usage of GNSS in those locations obsolete. Then we have the Lunar Communication and Navigation Services, or LCNS, which is a proposed constellation of 3 to 5 satellites orbiting around the Moon. Here, a publication by Antoine Gagnier showcases a 3 sigma precision of 30 meters for lunar landers. Applications such as autonomous rover navigation requires a higher accuracy than provided by LCNS alone. Here we're going to introduce visual odometry. The Perseverance rover features 19 cameras in total, which are being used for panoramic stitching, terrain modeling, obstacle detection, or visual odometry. With visual odometry, relative traverses can be estimated based on pixel movements. This is connected with the concept of simultaneous localization mapping, or short SLAM. SLAM constructs a map of an unknown environment while simultaneously keeping track of the robot pose within it. A popular implementation is OrbSLAM, which video is shown here. We can see that the blue frames correspond to the path of the camera and the dots correspond to the map that is being incrementally generated. A common feature of powerful SLAM is also the concept of loop closing optimization, where the position and the neighborhood of the map gets refined once the camera traveled back to a location it has been before. And using this method, step by step the map is being generated. A fusion between satellite and camera-based navigation makes sense due to their complementary nature. In particular, satellite navigation works best in outdoor, open-sky environments without any obstructions, whereas visual navigation works best in dense, urban, well-illuminated areas, where features can be tracked from one image to another. We want to make use of open-source SLAM libraries, and our initial thoughts were first if we should either adopt Earth-based visual libraries or reuse a library developed for Mars for lunar environments. Because of this, we selected 3 potential candidates, which are the following. First, there's OrbSLAM 2, which is an optimization-based SLAM and highly popular in the robotic research community. Then we have OpenVins, a filter-based SLAM that was released in 2019 with a lot of documentation. And last we have Spartan, a SLAM developed for operation on Mars and has been used at ESA TEC-MMA for various research projects. At the end, OpenVins was chosen because the usage of Spartan requires the installation and usage of the additional rock framework, which we do not have experience with. Second, we also figured that the distinction between Earth and Mars-based SLAM mostly impact computational costs in a sense that Mars-based SLAMs are optimized to use the least amount of computational effort. So there was no direct distinction in the visual processing of different environments. And lastly, OrbSLAM was not chosen because it does not report uncertainties compared to OpenVins, and we need these in order to assess the performance of our fusion. OpenVins is an open-source filtering-based visual-inertial SLAM algorithm which reports the positions and orientations of the rover as well as the uncertainties in the form of covariances. As can be seen in the video, by analyzing the motions of pixels in combination with inertial information, the path of the rover can be incrementally estimated. For input data, we found 4 available planetary datasets. First, we have the datasets which were produced at ESA. We have the Noordwijk dataset, which has been collected with the heavy-duty rover on the Noordwijk beach. ESA also gathered data with the same rover on the Tenerife island. However, this dataset is not yet publicly available right now. We also have access to an indoor dataset collected by TEC-MMA using their ExoMars testing rover. However, they come in rock binaries instead of raw formats. On the external side, we found a planetary dataset collected in Canada on a testbed using a smaller rover. This dataset was showcased to be very reliable and therefore was used for further analysis. Among many other sensors, the Canadian dataset contained data gathered from a monocular camera and an IMU. Furthermore, it entails the relevant intrinsic and extrinsic parameters for both sensors. For evaluation purposes, the dataset also includes ground truth RTK measurements. The goal of the evaluation framework is to implement user navigation algorithm and assess the performance possible using LCNS and GNSS, plus inertial and visual navigation techniques in a Lunar Rover scenario. We took the visual-inertial data from the Planetary dataset on one side and feed it through OpenVINS to generate visual-inertial pose and covariance estimates. On the other side, we took the RTK measurements and generate perturbed satellite-based positions and covariances. Both data streams are then fused using a loosely coupled Kalman filter in order to generate the combined poses and covariances. For the loosely coupled Kalman filter, we use an open source tool called Navigo. In its baseline framework, it implements a strapped-down inertial navigation system of which corrections are made using GNSS measurements through an error state Kalman filter. We extended this framework to take an additional source of visual inertial position and velocity measurements coming from OpenVINS. The strapped-down inertial navigation system of Navigo requires a knowledge of the noise parameters of the IMU, which among others include angle and velocity random walk, static and dynamic biases. In theory, those are estimated using an Allen variance analysis. However, this requires a collection of static IMU measurements over a long period of time. Our chosen dataset does not contain such a collection. Therefore, these parameters were determined using a brute force optimization procedure where a set of parameters which minimizes the least square position estimation error was picked. In the following, we are going to present the results of the evaluations. In the first step, we are testing the baseline by combining degraded GNSS with IMU only. The result for a satellite position degradation of 1 meter standard deviation can be seen in the top figures. Although the satellite data points are widespread, the combined version is able to estimate the ground truth trajectory reasonably well. This holds true even with a high satellite degradation of 5 meter standard deviation, as can be seen in the bottom figures. In a further step, the combination of OpenVINS with IMU was evaluated, as can be seen in this figure. Since OpenVINS already uses IMU for its position estimation step, it is expected that the trajectory of OpenVINS by itself and OpenVINS plus IMU are aligned. Furthermore, the accumulated drift from the ground truth, which increases over the traverse distance, can be observed. Lastly, the combined fusion of degraded GNSS with OpenVINS and IMU was evaluated. Here, the specific measurements of OpenVINS data and GNSS were weighted by multiplying the respective covariance matrices with a weight factor. Specifically, the OpenVINS covariances were manually increased by a factor of 10 to the power 5 in order to mitigate the drift effect. The results can be seen in the top figures, which showcase the mitigation of the drift compared to the previous baseline performance with the trade-off of being less smooth. In a second evaluation, GNSS data are partially removed along a tract of the trajectory, which simulates a scenario where LCNS satellites are not visible. Here, OpenVINS provides a robust fail-safe solution during the time span where no satellite navigation data are available. This can be seen in the bottom figures. One can also observe that the overall error reduces quickly once satellite data becomes available again. This concludes the current state of this project. In the future, we would like to test the existing framework with the Moon projected rover trajectory as well as with simulated lunar satellite orbits. Their respective software tools are part of previous developments at ESA. Moreover, it is to be investigated if a tight coupling between visual inertial and satellite data would potentially lead to better results.